Let's take a look at the convex optimization, the fifth topic of machine learning. Here, we will mainly look at the quadratic programming, QP. Quadratic programming is used in the support vector machines, which we will cover in the next topic. To better understand the support vector machines, you first need to know how to solve quadratic programming. First, let's look at an overview of the constrained linear programming LP and quadratic programming QP. This video was produced in Korean and translated into English. My voice was generated using AI text-to-speech. Let's take a look at the full table of contents. In the first video, we will look at concepts such as convex, linear, affine, constraint, and binding. We will then look at LP and QP problems with constraints and how to find solutions using graphical methods. In the second video, we will see how to use Lagrangian methods to find a solution to a QP problem with equality and inequality constraints. In the third video, we will look at how to solve EQP and IQP problems using the Dual Lagrange method. Lastly, in the fourth video, we'll look at the Slater condition and KKT condition, and look at how to solve EQP and IQP problems using the KKT method. And let's write code to find the solution to the optimization problem using the CVXOpt library. Let's look at the mathematical definition of the convex function. There is a function f of x that is convex downward. A real-valued function f of x is said to be convex. If the line segment AB between any two distinct points on the graph of the function lies above the graph between the 2 points. The mathematical definition of the convex function is as follows. Pick a t-weighted average point of x1 and x2. If t is 0, it is this point, and if t is 0.5, it is the midpoint. Then the value of the function f at this point is here. And the t-weighted average of f of x1 and f of x2 is this point. If this value is less than or equal to this value, the function f of x is convex. Conversely, a function that is convex upward is called concave. Next, let's look at the definition of a linear function. When there is a function f that maps from the domain Rm to the range Rn, if this equation holds true for any vectors x and y belonging to Rm, and if this equation holds true for any vectors x belonging to Rm and the scalar a, then the function f is called a linear function. Let me give you an example. There is a function f such that f of x is 3x. f2x plus 5y becomes 2fx plus 5f of y as follows. This satisfies all of the above definitions, so f is a linear function. A linear function has no intercept and passes through the origin. Next, let's look at the definition of the affine function. There are functions g and f that map from the domain Rm to the range Rn. We say a function g is affine if there is a linear function f and a vector b in Rn such that gx equals f of x plus b for all x in Rm. In other words, an affine function is just a linear function plus an intercept. Let me give you an example. There is a function g such that g of x equals 3x plus 5. Since the function 3x is a linear function, the function g is affine. Next, we will briefly look at concepts such as objective function, constraints, and feasible region. Let's look at a linear constrained optimization problem. We want to find argmin of this function with respect to x1 and x2. This is our objective function. This objective function can be written as follows. Even excluding the constant 5, the solutions of these two objective functions are the same. However, the min values of these two objective functions are different. And there are 4 constraints as shown below. Let's solve this problem graphically. The function f(x1, x2) is the equation of this plane. This is the plane that passes through the 3 points 3, 0, 0, and 0, 5, 0, and 0, 0, 5. And the normal vector of this plane is 5, 3, 3. Now let's draw the equations of the constraints one by one. The first constraint is the area to the left of this straight line. And the second constraint is the area to the left of this straight line. The third and fourth constraints are this area and this area. This is the region that satisfies all these conditions. This is called the feasible region. Extending this feasible region along the fx1, x2 axis results in a yellow square prism. The minimum point of this function within this region is this point. Therefore, the solutions to this optimization problem are x1 asterisk and x2 asterisk, which are 1 and 0, respectively. And the min value of this function is 10/3. Now let's see what this figure looks like from above. This is the feasible region on the x1 and x2 plane. And these lines are contour lines on the plane, getting lower towards the right. The point at which this contour first touches the feasible region, as it rises from low to high, is the solution to this optimization problem. These two constraints affect the solution. These are called active constraints, or binding. These two constraints do not affect the solution. These are called inactive constraints, or non-binding. This time we will look at the generalized mathematical representations of constrained linear programming and quadratic programming. Let's look at the linear programming problem below. The goal is to find the minimum value of this function. There are 5 constraints as shown below. There are 4 inequality constraints and 1 equality constraint. The standard form of this problem is as follows. Using the uppercase G and the H matrices, the inequality constraints are expressed as follows. And using the uppercase A and B matrices, the equality constraint is expressed as follows. The X, C, G, H, A, and B matrices are respectively as follows. Let's multiply the matrices G and X. The results are as follows. These results then become 4 inequality constraints on the left. Similarly, multiplying matrices A and X creates an equality constraint on the left. So we see that this standard form is equivalent to the original problem. This time, we will look at the quadratic programming problem. The goal is to find the minimum value of this function. There are three constraints as shown below. The standard form for this problem is as follows. As shown on the left, the G and H matrices are used to represent inequality constraints. And the A and B matrices are used to represent equality constraint. The X, P, Q, G, H, and B matrices for this problem are respectively as follows. Expressing LP or QP in a generalized form can standardize the procedure for finding a solution. From the next video, we will look at how to find a solution by converting the optimization problem to standard form. We will then write code to solve the optimization problem using the CVXOpt library. This time, we will solve a simple quadratic programming problem using a graph method and see how the solution changes depending on the constraints. Below are three types of optimization problems. The objective function is the same, but the constraints are different. These problems can be expressed in one standard form as follows. First, let's draw the objective function in three-dimensional space. The objective function is a paraboloid like this. Next, let's draw a straight line with the constraint x1 plus x2 equals 1. This line is on the x1 and x2 plane. If we extend this straight line up along the f-axis, we can see that the paraboloid is cut by this plane like this. The solution to the first optimization problem, A, lies at this point. This gray plane is the feasible region for A. And this point is the point in that region where the objective function value is the smallest. The solution to the second optimization problem, B, lies at this point. This is because the region to the left of this gray surface is the feasible region for B. And this is the point in this region where the objective function value is the smallest. The solution to the third optimization problem, C, is also at this point. This is because the area to the right of this gray plane is the feasible region for C. And this is the point in this region where the objective function value is the smallest. Now let's take a look at the view from above. The paraboloid, which is the objective function, can be drawn as contour circles like this. The further you go in, the lower the contour level becomes. And this is the line of x1 plus x2 equals 1. The solution to the first optimization problem, A, is at this point. This is because the points on the red straight line are the feasible region for A. And the point where this straight line meets the contour line is the solution. The solution to the second optimization problem, B, is at this point. This is because the area to the left of the red straight line is the feasible region for B. And the lowest contour in this region is at this point. The solution to the third optimization problem, C, is also at this point. This is because the area to the right of the red straight line is the feasible region for C. And the lowest contour in this region is at this point. And the objective function looks like this when viewed from the right. The solution is at this point or at this point. Since the view from above is easy to interpret, we will use this figure from now on. Since the location of the solution varies depending on the constraints, it becomes difficult to find the solution when there are many or complex constraints. From the next video, we will look at the generalized methods to find solutions for each case one by one. For reference, let's write code that draws the objective function from the previous page in three-dimensional space. This code has already been used in linear regression and logistic regression. Here, we will only check the results. The results are as follows. Multiple points were generated using the mesh grid on the x1 and x2 plane. And the values of function f for each point were calculated and plotted. We can see that both objective functions are convex downward. Let's run this code. The results are as follows. So far, we looked at an overview of constrained convex optimization problems and looked at the graphical solutions for simple problems. In the next video, we will look at how to solve the EQP and IQP problems using the Lagrange method.